Hello, my physics fanatics. Here's your answers to the Forces Quiz Review. This is a great resource to use for your quiz that you're taking about forces. So here we go. Number 1. SpongeBob. He's pushing a box of Krabby Patties across the floor at a constant velocity. The box weighs 110 newtons and he's pushing with a force of 98 newtons. So for this one, the directions say to draw a free body diagram and then to calculate the net force. So I know that this box of Krabby Patties is on Earth, meaning that there's a gravitational pull on the box of Krabby Patties by Earth, and that's called the weight of the object, or Fg. And we were told that that weight is 110 newtons. Now, the box is not falling through the ground and it's not levitating, so there must be an opposite force acting on this box. In this case, it's the normal force because it says the box is resting on a surface. He's pushing, that's an applied force, with a force of 98 newtons. And the problem told us that the box was moving at a constant velocity. A constant velocity means the box is not speeding up or slowing down, so the acceleration is 0. And in this case, all of the forces must balance out. If acceleration is 0, net force has to be 0. So the friction acting on the box is also 98 newtons. So in this case, we have balanced forces, but the object is still moving. It's just moving at a constant velocity, not accelerating. Number 2. Squidward, he's practicing his clarinet. His clarinet falls off the roof. So free body diagram, gravity. The weight of that clarinet is going to drag it back down to Earth. And it tells us that that force is equal to 7.3 newtons. And we're also told that there's 0.75 newtons of air resistance. I'm going to draw a smaller arrow up. Air resistance opposes gravitational force of 0.75 newtons. And in this case, the net force, there are no horizontal forces in play here, just vertical. So we would subtract those two, 7.3 minus 0.75, to get 6.55 newtons. 0.6. Now, force is a vector. So you would say down, you'd add a direction, or you can put a negative sign there. So there's some extra force acting downward, meaning the clarinet will be accelerating downward until it hits its terminal velocity. Number 3, Mrs. Puff, she's going for a ride in her boat. We assume this boat is on land. If you look at the GIF that's on the picture, it shows you that she's driving her boat on a road. So it tells us that the applied force on this boat is 240 newtons. The force of air resistance that would act in the opposite direction as she's pushing against air is 24 newtons. And then there's also a second opposing force of friction. So you draw it like this. You just put the arrows end to end. And that force of friction is 12 newtons. So I should have drawn this arrow much larger to show scale here. Obviously much more force in the applied direction. So to calculate the net force, I'm going to take 12 plus 24, that's 36, acting in the negative direction, and subtract it from 240. So 204 newtons, and that would be in the positive direction. Number 4. The hash-slinging Slasher is running to the Krusty Krab to drop off his application. He runs with an applied force of 250 newtons, so I'm going to draw that in the positive direction. And there's a force of friction and air resistance. Those two forces, so FF plus FA, are equal to 19 newtons. So this is very similar to the last one. You just subtract 250 minus 19. Gives you a net force of 231 in the positive direction. Number 5. I don't think I'm going to write this one out. This one says, what is Newton's first law state? So this one, hopefully, you were able to find it in the notes. It's an object at rest stays at rest, object in motion stays in motion at a constant velocity unless an outside force acts on it. Number 6, describe how we experience Newton's first law as we ride in a vehicle. What's your body want to do every time the car speeds up? When a car speeds up, you tend to go backwards. Your body tends to move backwards. And when the car slows down, your body tends to move forward. And that's because your body is keeping that constant velocity that the car had before it accelerated or braked, or applied the brakes. So let's jump to number 7. A force of 600 newtons is applied to a 40 kilogram bike. I'm going to start making my free body diagram first. So I know there's going to be I'm going to have to calculate net force. So 600 newtons of applied force on this 40 kilogram bike. That's my mass. What acceleration is produced, so A is the unknown, if there's a force of friction of 30 newtons acting in the opposite direction, that's friction. So here you would have to first find the net force. So 600 minus 30 is 570 newtons. Then you can use Newton's second law, F equals ma. 570, so you'd have to divide by the mass to get an acceleration of 14.25 meters per second squared, and that's in the positive direction. Number 8. Penguin sliding down a hill, or sliding across snow. Mass of the penguin is 23.15 kilograms. The penguin is accelerating at 1.2 meters per second squared in the positive direction. So first I would need to find the net force. I'm going to draw out the free body diagram. I don't know what these forces are yet. The values. I do know that they are friction and the applied force, though. So to find net force, we can use Newton's second law. 23.15 times 1.2. So the overall net force here is going to be 27.78 newtons, and I know that's going to be positive. So that means we're going to have 27.78 extra newtons of force over here. So then the second part of the question, it tells us that the value of the friction is 11.3 newtons. So I know that net force is equal to FA minus FF. And I just solved for the net force. 27.78 equals FA is my unknown, that's what I'm looking for here, minus the friction is 11.3. So we would add to isolate FA. 27.78 plus 11.3 gives us 39.08 newtons. So that's what our force would be here. Okay? That is positive. All right, number 9 and 10, there are no math here. So number 9 is for every action, there's an equal and opposite reaction is the third law. So an example for number 10 of an action-reaction pair. Just think of any force acting on any two objects. So for instance, my water bottle sitting on my table here. There's a force exerted on the table by the water bottle, and there's an equal and opposite force exerted on the water bottle by the table. That would be one example. All right, hope this helps.